Hey everybody, let's continue with this introduction to calculus. Today it's going to be all about rates of change. Now, rate of change, we could really just call that the slope of a function over a certain interval. And I'm sure you're very familiar with the idea of rise over run. This is kind of the core of, grade 9 and 10 math in terms of working with linear equations. So rise is really just looking at our y values, the change in our y values, and this triangle just refers to the change. And run is the change in our x values. So if I were to pick 2 points on this graph, let's go with 0, 0, and maybe 2, 4. The equation for rise over run is going to be y2 minus y1 over x2 minus x1. So if I write out the coordinates to my points, I'm going to pick the point further to the right as my second value. So this is my x1 and y1. And if I plug in my values, I get 4 over 2, which is a slope of 2. And that makes sense because the equation for this line is y equals 2x. So if I look at like the general term for a line, or the general form of y equals mx plus b, I can see that m refers to my slope of 2 and b refers to my y-intercept of 0. Okay, that's all fine and good. The problem is when we're dealing with more complicated functions and we try to apply the same logic, right? Because if I look at this quadratic, which has the equation y equals x squared, if I plug in a 0, I get a y value of 0, which is why our origin is down here. And then if I plug in a 2, I get a 4. So the same 2 points exist on the quadratic as the linear equation. So in theory, I could do rise over run using the exact same points and get the same value of 2. So basically what I'm saying is if I took a line cutting through those 2 points, that would be the slope of this line. So we would call that the secant between these 2 points. The problem with that is it's not really accurate to the changing slope that's occurring here. Sure, it's accurate between these 2 points, but we can see that the slope of this graph, of this quadratic, is changing very rapidly. So if I wanted a more accurate measurement of the slope at a certain point on this graph, how would I do that? Well, we can use a smaller interval. So instead of picking such a large range for my points of like 0, 0, and 2, 4, I could do something a lot closer to each other. So for example, let's do the point 1, 1, and maybe the point, let's say 1.5, 2.25. Because if I plug in a 1.5 and I square the value, that's what I'm going to get. So let's try that again. This is going to give me a 1.25 over 0.5, which turns out to be a 2.5. So that tells me that the slope between these 2 points here is 2.5. So you can see how we've created a larger slope, which is more accurate to what's going on with the quadratic in that area, by using a smaller interval for our x values. So this brings us to kind of the clashing point between rate of change and limits, which we went over last video. And let's take a look at this quadratic. So run refers to the change in my x value, and rise refers to the change in my y value. What if I were to set a limit of my run approaching 0? That's an interesting thing to think about. So if I'm just going to redraw this to the side here, where I'm picking 2 points and I have my rise over run. So if I think of rise over run with respect to run as a variable, let's apply it as an h. I could say that my rise could be the value of the function at x plus h minus the original value of the function. So all this is, you can think of this as our y2 value. So back here in our slope equation, this would be our y1 value, because I'm taking the value of the function at my original point, or at my starting point, and I'm subtracting that from the value of my function when I consider the run being applied, or the change in x. And so what I could do is I could rewrite my slope equation as fx plus h minus f of x. This refers to our rise over our run, which we've just shown as a variable h. And this is just that equation rewritten. So what this can do is, we have rise over run represented a new way. If we set the value of h to be approaching 0, we could technically find the instantaneous rate of change for a function. Because looking back at the quadratic, if I were to effectively set my run as approaching 0, basically what's happening is I'm making the intervals become smaller and smaller until basically what I'm doing is I'm figuring out the slope of the tangent at a single point for that quadratic. So as h approaches 0, this is basically what's happening with our interval. And we're getting closer and closer to the most accurate representation of slope, at least instantaneous slope. So this is basically how we would write out for instantaneous rate of change. We have our rise over run equation here, and we're setting the limit of h as it approaches 0. The problem is, and this is a very similar problem that we had in the previous video, we have a variable in our denominator that if we set equal to 0, we don't really have a function to work with because we can't divide by 0. So what we need to do is we need to find a way to rearrange this function, or to expand this, and to actually eliminate h in our denominator. So let me show you how we'll do that with this example right here. So we're going to use this formula to solve for the slope of x squared plus 5, which is a quadratic, when x equals 2. So the first thing I want to do is I want to actually just plug in the value of 2 into the equation, because I'm going to need the value of f of x at 2. So let's do that over here. And we get a value of 9. Okay, so let's start writing out our equation here. Now fx plus h, to fill in this part of the equation, I'm just going to rewrite f of x, but with h as well as a variable. So that's going to look something like this. X plus h squared plus 5 minus f of x, which we figured out has a value of 9, over h. Now, if you notice here, I have an x and an h value, which is going to make it hard to kind of work with. I want to remove as many variables as possible. So what I'll do, I'll just set the x value as equal to 2 here. So now all I have to work with is h as a variable. And what I can do is I can actually expand this 2 plus h squared. And that's just following the FOIL method. So I could just write it out kind of like this, and then expand it out. And that will give me a 4 plus 2h plus h squared. And then I've just got the rest of my values over there. You'll notice here, if I collect my constant numbers, my regular values, 4 plus 5 is 9, minus 9 is 0. So I can actually just get rid of all of that. And I'm left with a 2h plus h squared over h. And what I can do is I can actually factor out an h on my numerator. So let's continue. So I factor out the h, and look at that. I can cancel out the h on the denominator because I have a value of h isolated up here as well. Now I can actually set h to 0 because it's not going to screw up the function. It's just going to be set to a value of 0, so I can see that the instantaneous rate of change is 2 when x equals 2. Now, we solved this when we had a value of x. So we kind of know the point on the quadratic for the slope that we're solving for. But what if we want a general function where we could use any value of x and we would figure out the instantaneous rate of change? For that, we need what's called a derivative. And a derivative is a function on its own that's going to tell you the rate of change for any value of x on the function. So it's very similar to what we just did, where we're going to have to use this equation here. And this notation here of just having this little notch refers to when we're solving for a derivative. So the steps are going to be very similar to what we just did. However, instead of actually plugging in a value for x, we're going to leave the variable alone. So basically what that means is when I plug in my value for f of x, I'm just going to leave it as the function itself. So let's set this as x plus h minus the function itself over h. And what we're going to do here is we're basically just going to expand out everything on our numerator. So again, I can FOIL out this whole chunk here. I'm going to get a x squared plus 2xh plus h squared and now I just need to kind of apply this 4 to everything inside my brackets. So let me do that. Running out of space, but bear with me. So this is going to give me a 4x squared plus 8xh plus 4h squared. And I can kind of cancel out these 8's because I have a positive 8 and negative 8. Those will set out to 0. And then here as well, I have a 4x squared here and a minus 4x squared here. So those will cancel each other out. And in my two terms that are left on my numerator, they both have an h as a variable, so I can factor that out. And once again, just like the previous example, I can get rid of the h on my denominator. I can now finally set h to 0, and what I'm left with is 8x. So the derivative of f of x being 4x squared plus 8, is 8x. And what that means is I can plug in any value of x here and actually solve for the instantaneous rate of change at that point on the function. So for example, let's say I wanted to figure out what the slope is when x equals 3. I'm just going to plug that value in, and I see that it's a value of 24. So this is basically the proof or the long way of how we create a derivative, how we find a derivative. In the next video, I'm going to go over some rules and some tips to be able to do this in a much faster way. So thanks for watching, and see you in the next video.